All right. So in the last lecture, we kind of like knowing that the modern processor architecture is pretty much like this. So for each of the processor, um, you have a superscalar pipeline, and with multi-issue capability, although older execution capability, but still maintain the correctness of your program through reloaded buffer. But even with that, we also figure out that in a lot of cases, we are not able to fully utilize our processor resource. So it turns out what happened is that we make our processor multi-threaded in a way that within each core, we have simultaneous multi-threading to present an illusion to the rest of the world, saying that even though there is a single pipeline, we now have two front end or multiple front end for you to schedule your programs, and internally we will figure out which instruction is coming from which program and make sure that the execution result is correct. On the other hand, we also notice that if we want to make a superscalar processor to be even more crazily multi-issued, then the hardware complexity is really, really high. So instead of keep growing the issue width of a superscalar processor, we decided that maybe we should just choose the option of duplicating the processor core so that we are able to provide another level of parallelism called thread level parallelism in a different way. However, the key of using thread level parallelism to speed up a single program is to multi-threading your program. However, to maintain the correctness of your program, we still need some kind of underlying hardware support. For example, the coherence protocol and consistency protocol to make sure that at least the programmer can predict in some degree what's going to happen. However, even with that, there are still issues that we need to be really careful about when we partition our tasks. For example, now because you have the coherence protocol running, so we are running into the problem of coherence miss. And there are coherence misses in true sharing, meaning that multiple threads, they are indeed using the same memory address. Or false sharing, meaning that they are not using the same address, but just because of the coincidences that the address that multiple processors need to access are coming from the same block, then one will invalidate another one. So, and even though we get that addressed, there are still issues like this because your processor will internally perform out-of-order scheduling, as well as the compiler can potentially reorder instructions based on their data flow. So what do you see is, and what do you think is not what you get? So it turns out that you will have to have consistency protocol to make sure that for some set of instructions, they should be at least performed in the order that we want. However, what does that mean is that it also decreased the freedom of reordering in terms so that we would lose the performance. So what we want to say is that although a lot of people think, well, parallelism should come natural. However, that's never true. In fact, parallel programming is very hard because you have to be aware the cache coherence issue and cache consistency issue, and also the processor behavior is also not deterministic in a way that you cannot predict which processor is making faster progress. You cannot predict when the operating system is going to schedule your thread. You cannot predict when the processor is going to schedule an instruction. So all sorts of this is just telling us parallel programming is hard. And in addition to the scalar type parallelism, in addition to parallel your program using thread, Another thing to think about is that there are some mathematical operations that are implicitly parallel. So for example, for measures operation, all pairs of scalar data within the same vector, they are supposed to perform the same operation if you are performing vector algebra. So it turns out, and because the commonality of vector algebra in many mathematical kernels, so it turns out modern processors like Intel Alder Lake processors, they have this FMA, like a vector unit that would allow multiplication and accumulation in a vector fashion, which allow us to speed up some of the key operations like vector multiplication or meshes vector operations that are key to our machine learning algorithms. So as a summary, right now, our processors, modern processors, they offer parallelisms in several different levels. So from the same program, the same thread, the processor can exploit instruction level parallelism through superscalar, through pipelining. For thread level parallelism, if you are able to parallelize your program with multiple threads, then we can use simultaneous multi-threading or chip multiprocessor to run them concurrently. Even though you cannot create them as a thread, try to think if you can vectorize them or matricize them, then you will be able to get the data level parallelism. So these are the 3-level parallelism. And today we are going to talk about how modern world uses multi-core processors and the dark silicon problem, which is preventing us from getting better performance out of these processors, and how are we going to tackle the issues in dark silicon era. So you probably read this paper, Web Search for a Planet, the Google Cluster Architecture, which is published in 2003. So through this paper, let me see. So through this paper, this is a very interesting paper because one thing that you can find is that a lot of people think, well, Google is successful because their service is the best. But in reality, I want to tell you, in terms of search performance, Google is never the best in the era that Google was just a startup. And the best search engine is actually Alta Vista at that time. And the Alta Vista, they actually built very good servers, RISC servers, very expensive workstation to power their service. Their search latency is super short. However, they later beaten by this Google company, which was a small company at that time, but right now a big company. Believe it or not, in the very earliest 21st century, Google was once being considered sold to Yahoo. But that business never happened. Otherwise, Yahoo is probably going to be the largest company still. But at that moment, Yahoo signed a contract with Alta Vista because they think Alta Vista has better performance. But turns out both companies sync later on, right? But what's the reason? So the success of Google's data center is not because Google is a company don't do evil. It's not because the company is offering the best performance. It's because they did the right thing. So what is the right thing to do? So what I think is that, well, first of all, performance price beats peak performance. So what does that mean is that Google won over other companies just because they know how to save money. That's the trick. They know how to save money as well as earn more money. So Google is not a company provide customer service. It's never a company who consider customer as their top priority. They consider money as their top priority. That's about Google, right? So not the CPU that gives the best absolute performance. And the second thing you will find, the second principle they use is use commodity PCs to reduce the cost of computation, right? So another company which becomes a superstar at that time. Before Google goes up, the most significant server company is actually Sun. I don't know how many of you heard about it, but if today you go to the backside of the Meta Menlo Park campus, they still reserve the sign of sun to that people not forgetting about the story of how the company become failed. Right. So, but Sun was once the largest server company. And the processor they use is from a company called Digital Equipment Corporation. And you never heard about those companies, right? Because they all being acquired by some other company later, right? But why? Because companies like Google, they chose to use commodity PCs. And who is their collaborator? Dell. And before Google selecting Dell, Dell was also a company startup from a garage in the Bay Area. And they assemble their computers inside a garage, send it out. But after they won a Google contract, it becomes a different company. It's pretty much like the story of Supermicro with NVIDIA these days, right? So, but again, right, employ more expensive techniques in our ranking algorithm or search for larger index of document, right? So the thing is that they would rather spend the same amount of money with more computers to compensate the fact that they don't have a good computer. Software reliability. So at that moment, people saying that they want to provide the best service. So server like DEX and Sun solution, they all have RAID, which and SCSI-based RAID, which offer you very reliable hard disk drives. However, what Google selects is just like those like Seagate or Western Digital, like very cheap hard drive that you can purchase from the market at the same time. And what they do is that they use software reliability by detecting the errors of this hard drive. And whenever they detect an error, they just shut it down. So if they shut it down, how can they maintain a service? Replications, right? So that they produce a lot of replications of the same content. So if one machine shuts down, they can just use another machine to replace the functionality or cover the functionality of the machine that failed, right? And the thing is that if you don't have to build a RAID, instead of that, you just purchase some very cheap like IDE hard drive at that time, you can actually have larger capacity and which is large enough for you to have many replications of your data. So that's how Google success. It's a company knows how to control the cost. It's a company knows how to use the lowest amount of money to give you the service at an acceptable level. All right. So in that kind of company, what kind of processor do you think they chose at that time? All right, let's take a look. Okay, so, I love this figure because it tells me that you guys probably didn't read the paper and you forgot what's the paper about. So why don't you guys go ahead and refresh your mind regarding what Google have revealed in the processor spec they want in their papers. All right, so let's take a look. So after discussion, more of you think it's C. So what are the two that you guys have in mind? Is the first one correct? Do they want a processor with as many? So how do you interpret the first sentence? What it wants? IOP, instruction level parallelism, right? Because it says we want to execute as many instructions as possible from the same process, the same thread. So that's instruction level parallelism. What did the paper say about instruction level parallelism? What did the paper say about the instruction level parallelism? Diminishing returns, right? So there isn't that much exploitable instruction level parallelism. It's not about diminishing returns, right? So it's actually talking about because the program itself doesn't have instruction level parallelism. So why do you need a processor with a lot of instruction level parallelism? How about the second? Do we want a processor with as many like process and threads simultaneously being executed? So what kind of parallelism is this sentence referring to? What kind of parallelism is this sentence referring to? What kind of parallelism is this sentence referring to? Which level of parallelism? Which level of parallelism? Which level of parallelism? Which level of parallelism? Thread level parallelism, right? So regarding thread level parallelism, what does the paper say, right? Exploiting abundant thread level parallelism at microarchitecture appears equally promising, right? So what does that mean? They want a processor with rich thread level parallelism. How about branch? Where can you find that in a paper? What about branch? What about branch? What does the paper say? Okay, so why we need to read a paper? Why do we need to read a paper? And why don't you read a paper? Right, so here's the main thing. Sometimes we assign paper to you because they are delivering key insights that the textbook is not telling you. The textbook only tells you the fundamentals. However, for the case studies, today, if your company wants you to say, well, I want to build a service like Google Search. If you don't read this paper, you will probably thinking about, why don't I just buy an NVIDIA like AI server to power this service? But after you read this server, do we need an NVIDIA GPU for this thing? Not at all. What do you want? A very cheap computer, low instruction level parallelism, rich thread level parallelism, right? But how about a branch, right? We need a processor with lower misprediction penalties or lower misprediction rate. Branch matters, right? I see a lot of you like shaking your heads. So I can tell you didn't read a paper. You're just guessing. How about the fourth one? Large cache capacity? No. Is this what the paper said? You believe so? The paper said that? Right. So the answer is a memory system with a relatively modest size, L2, short L2 cache and memory latencies, longer cache lines is likely to be the most effective. It doesn't have anything to do with what you just said. Right? So don't use your own intuition in system design. Don't use your intuition in system design. Read the paper. Right? There is a paper talking about this system and why they make these decisions. You will figure out it's very counterintuitive. In a lot of cases, when we make decisions, we think we want a processor with larger cache. It will give you the performance anyway. No. They say a good enough cache size is already satisfying for their search. You might think, I don't care about branch prediction. In fact, thinking about the nature of cache, a search, it actually relies on a lot of decision process to determine if I want to look into this document or not. Why branch prediction isn't important, right? And a lot of you might think, okay, processor with good superscalar capability would help me getting better performance. But thinking about this, if you have a program with a lot of branches, does ILP matter? You are probably going to have your low ILP anyway, unless you can figure out to predict this irregular search behavior perfectly, which is very difficult, right? So it turns out based on that, I mean, the answer is C, but this two may be different from the two that you are thinking. And how do you know what are the right two? Read a paper, please. Okay? And one thing I have to warn you, in a final exam, I would ask you to read some papers on the spot and figure out the right system design. what kind of processors. So if you don't develop the capability of how to capture the point of a paper really fast throughout the quarter, you will run yourself into trouble in the final exam. I'm serious. I'm very, very serious about this. All right. So another thing which I think is very interesting about this paper is that they talk about in evaluating the data center design, what they care. They care about the cost, right? They talk about money everywhere. So the successful story behind Google is never because they treat their employee very well. It's never because they have the most innovative algorithm. No, they have nothing but the trick regarding how to save the cost, right? And so in data center design, they care about power, they care about energy, they care about space efficiency. But why they care about space efficiency? So why they care about the power? They care because power is related to the cost of heating. Again, the cost. What about energy? Related to the cost of electricity bill. Again, it's about money. Space efficiency. The space overhead in storing every bit of data. Why they care about this? It's related to how many hard disk drive you need to purchase. Again, about money, right? Throughput, reliability, right? Because that's probably the basic requirement for powering up a service. But other than the last two, everything else is all about the cost, right? And right now, regarding the cost, there is a significant increasing concern on this thing called like carbon footprint emission, right? So, and in fact, in Google's vision in 2030, they need to figure out how to achieve net zero emission. Otherwise, there will be a carbon footprint tax being charged for their data center services, right? So this is another thing that's increasingly important in data center design nowadays, right? And we will going to touch that issue later. But for now, let's talk about another thing called dark silicon. So previously we mentioned Moore's law. So the idea of Moore's law is that the density of the silicon double every 2 years. And if you follow that, based on the process technology we have, we are still able to barely catch up that trend. However, even though we catch up that trend, there's still a problem. So read through the sentence here and tell me about what the problem is going to affect. All right, so let's take a look. Okay, so definitely we need some discussion. So why don't you guys talk to each other regarding what do you guys think? All right, so let's take a look. So, okay, after discussion, more of you think the answer is E. So, first of all, how about the first statement? The power consumption per chip will increase. True or false? How about the second? The power density of the chip will increase. Right? So take a look of this, right? So saying that, well, before we scale it to the next node, process node, right? Saying that I have a 94 transistor chip, and each chip I have each transistor I have like 1 watt of power. Then that means that I would have like 49 power in total, 49 watt power in total, right? And now saying that I scale to the next node, which give me twice of the density, right? Then, however, with the broken denote scaling, meaning that we are able to scale down the size of the transistor, but the power consumption per transistor remains the same, which is pretty much the assumption of this question. Then you can consider the fact that we are going to have twice the amount of transistor, for example, 100, and each transistor still costs 1 watt of power. So it turns out that we are going to consume twice the amount of power, right? And if you look at a square like this one, right, then you will figure out that, okay, within the same area, we are also consuming twice the amount of power. So, which means that the density goes up, right? So, in fact, the density would actually challenge the way how we would dissipate the heat, right? So, and tell you the truth, in early 2000, we are already reaching the same heat density as a nuclear power plant. So what does that mean is that if we keep growing the density of the chip, your power density will also goes up. People would predict it to be as hot as the sun's surface, right? However, that's never going to happen because we are never going to never going to be able to dissipate the heat of the sun. So we have to maintain the same power density. So to maintain power density, right, what can we do, right? So then one of the options is that we just can only power up half of them, right? So then within the same area, we are still able to maintain the same power budget. So what does that mean? Even though we can build larger chip, or say within the same area, we are able to put in more transistors, those new transistors won't be able to contribute to our performance, right? So that's an option. And if we build that kind of chip, half of them will become dark. So that's why we have the name of dark silicon problem, meaning that we are able to build chips with more transistors, but we cannot let them all on at the same time. So some of them will become dark. That's called dark silicon problem. So it reminded me of the story a few years ago, well, probably also last year in the Bay Area, right? Whenever it's summer, right, we would have the power outage problem because everyone would turn on the AC. However, the power supply by PG&E is never sufficient to power on all the Bay Area because of the restriction in California. We have to use like renewable energy. We have to use very clean energy. So the speed of scale up the power plant is actually not being able to catch up the growth of the demand of data centers, of human beings in the Bay Area. So it turns out what happened is that we have to power off some of you during the nighttime. And like some friends of mine, they are in Sunnyvale, and they say, well, our places definitely don't have any power for 2 days. And some of them are thinking about like, okay, going somewhere like the company to work. So because companies typically have their own power plant. But then another fact they figure out because they have a Tesla, which also rely on the power to power, right? So they cannot even leave their home, right? So that's a pretty bad thing, right? So another option is actually, why don't we just provide each of the house or each of the transistor with lower power, so everyone would be able to maintain some basic functionality, but not at the full capability, right? So that's another thought, right? And why the idea of lowering the transistor power can happen is because if you look at the power consumption in each transistor, they actually compose of two parts. The first part is called dynamic power. So dynamic power is composed of these elements. So alpha means the average switching rate, and C means the capacitance of each transistor, and voltage squared means the supply voltage, and this F means frequency. So as you can imagine, if we are able to lower the voltage or the frequency go into each transistor, we are able to reduce the dynamic power, right? So one way to lower the power consumption of transistor is actually just running your processor or your transistor at a lower frequency, right? So that's what I meant to say. I give you lower power supply, and you run the transistor at a lower speed. So we can still deliver something, but not at your full capacity, right? And another power is called leakage power, or say static power. So one thing you need to be aware is that nothing is perfect. Nothing is perfect, right? So every transistor, they will potentially leak electricity when it's connecting to electricity, right? So what does that mean is whenever you start to power on your transistor, it starts to also leak some of electricity because of the imperfection of your material. And the leakage power is also related to your voltage supply, right? So what does that mean is that the most effective way to reduce the power consumption is to lower the voltage, but that comes with the cost that you also have to lower your frequency. And the other thing is that you cannot indefinitely lower your voltage, because if you have some electronical engineering background, you would know that to judge if the content within a transistor is 1 or 0, you need to have a clear threshold voltage that allow us to judge that. So what does that mean is that you can never lower your voltage below that. Otherwise, everything will be just treated as 0. Right? So what does that mean is that there is a limitation of how much voltage you can lower it down. Right? So the truth right now is that Moore's law now allow higher frequencies and making transistors smaller. But because of the power consumption issue, especially we are not able to make the power consumption lower. So even though we have more transistors, we have to lower their voltage so they become really slow, or we have to power them off. Right? So regarding this, everything here is true, right? But their implication here is, now we have more transistors. So theoretically, we can build many core processors within the same area. However, we didn't do that because if we put many core processors, you can only turn on some of them at their full speed, or you have to operate all of them at a slower speed, making the use of many core processors even more difficult. Right? It's already difficult in terms of programming, but right now it's even more difficult because you need to parallelize them, but also make them run efficiently for each thread, which is very unlikely to happen. Right? So the next takeaway here during the dark silicon era is that even though we can address all programming challenges, multi-core performance has stopped to scale because of the dark silicon problem. So this is a very important critical issue nowadays, because what does that mean? We are reaching a dead end. Don't you feel that way? Even though I spend a lot of time parallelizing my program, it's not going to be faster because the multi-core processor is not getting any faster. Right? So that's the dark silicon problem. Right? So regarding dark silicon, conventionally right now, we can, my explanation of the dark silicon problem, because it's a problem, right? So we should have a clear definition. So what's the problem about? The definition of a dark silicon problem is that you're given the same area, twice the amount of transistors, and the same power budget, a certain applications, how to maximize the performance of these applications within the given constraints. So given the first 3 constraints, how can you optimize the performance of a set of applications? That's the dark silicon problem. Right? So several ways you can do it, right? So for example, the earliest one we talk about is that we just accept the fact that it's dark. So we run some of the transistor at the top speed and not functioning some of them. And the other is some of them running slightly faster, some of them slower. And maybe another option is we just make them all slower. Right? And based on these options, how are we going to optimize the application performance? Right? So that's the dark silicon problem. Right? So let's start with the first one. So the first option is that we can have some of the transistors running faster, some of them running slower. So saying that if we are able to build a quad-core processor like this one, right, then the option is that we could have maybe 2 of the processor running faster, 2 of the processor running slower, right? So if we have a compute-intensive program, then we should schedule or automatically power up the processor running that compute-intensive program. And for memory-intensive workloads, once we detect it's running on a certain processor core, we slow down the processor core, right? For example, right? So in fact, this is a pretty common thing, right? So right now, and I think you already experienced that in your assignment 1, is that our processor, you can dynamically adjust its frequency, right? So for example, like the 10th generation of the Intel Alder Lake processor that you guys have been using in your assignments, it actually go from 800 megahertz to 5 gigahertz. This example, right? And then this is and like in a spec, it also mentioned that the max turbo frequency is at 5 gigahertz, and there is a technology called turbo boost. But this is nothing but Intel's hardware optimizer that automatically detect the workload to decide the frequency of each processor. It has been good for a while. I thought they have it fixed, and so that's the spec of modern Intel processors. So as you can see, they started to and also this is not a unique thing for Intel processor. Like even like AMD processor, they also have quite a wide range of frequencies that you can adjust. And the reason why adjusting frequency is an option is that because the frequency has some meaning to the performance, to the power consumption as well. Right. However, the thing is, if we, so if today our workloads is latency sensitive and do not have a lot of parallelism, this will work, right? However, thinking about those slow processors, right? Slow processors, it's very giant, but it's making very, very slow progress, right? So the efficiency of those parts, they are not very well, right? So, and another thing to think about, right, is actually, okay, so so another thing to think about is that why don't we just make all processor cores slower, but allow more processor cores, right? So, and in fact, in many server options, we will see that. So if you check Intel's offering, you will figure out that, well, Intel does have processors with 60 cores, which is a lot. However, I would never be happy with this processor cores because if you check the frequency of each processor core, it's basically 1.9 gigahertz, right? But if you have like a 8-core processor, it can run at 3.7 gigahertz. So in a lot of cases, students, they were pretty happy with when they see a server with many, many cores. But you know, these are the students who doesn't know architecture. Because if you know computer architecture, you will figure out sometimes many core processors is never your best friend because each thread is going to be running terribly slow, right? So that's the thing, right? And once Intel has a Xeon Phi processor, it has 72 cores, but if you look at the frequency, it's only 1.5 gigahertz. So it tells you that Intel does have the capability to produce processor with close to 100 threads, but they don't do it for a reason. Because if they do that, it means that each thread is going to run very, very slow. So, but is running slower always a good thing to power? So why don't you think about this way? Okay, so let's take a look. Okay, I like this figure because it means that we want some discussion. So why don't you guys go ahead and do that? Okay, so let's take a look. Okay, after discussion, more of you think the answer is C. So, first of all, right? So let's talk a little bit about the difference between power and energy, right? So we refer to the fact that lower power consumption by using the lower frequency, right? So some of you wonder, why don't we just always run the processor at the lower speed, right? Or what's the drawback of running the processor at a lower speed? So before we talk about that, we need to have a clear idea about the concept of power and energy and carbon footprint emission. So what is the power? So power is the direct contributor of heat. And as we mentioned, it's at this moment, how much electricity being consumed at the moment, right? So it's the moment, it's a measurement of the moment. And what does that mean is that if I drain a lot of electricity at a single period of time, it means that I would have to generate a lot of outcome within that period of time. Also means that I'm going to generate a lot of heat, right? So what does that mean is that the power contributes to heat, so it will affect the dissipation cost. It will affect what's the packaging of your chip, right? So if your chip is not using the right packaging, then it will get burned, right? So that's the problem, right? And also, what is energy? So energy is the total amount of power being drained during a period of time, right? So the equation of energy is power times execution time, right? So what does that mean is that this how much electricity bill you have to pay is based on the energy being drained, right? What does that mean is that your capacity, battery life is also depending on how much energy being drained, right? So a lot of misconception people would have is that, well, if I lower the power consumption, I can definitely lower the energy consumption, making my battery life longer. And that's not true. Because if you think about this, the energy is computed by power consumption multiplied by the execution time. If you cannot lower your power enough, but making your execution time a lot longer, you are actually going to create more energy consumption. Right? So this is another draw of that, right? So the blue one is the power. If I could have that the power goes up significantly to cover some of the early phase, then maybe I only need this amount of time. However, if I bottleneck my power consumption to be at this point, but turns out that you have to run the program longer, then as you can imagine, the green area is going to be larger than the blue area, meaning that your energy drain is going to be more in the lower frequency setting. And a lot of you might be curious about what's carbon footprint emission. So carbon footprint emission is about at what time from where I draw the power from. So saying that if in the daytime, then the power goes up, that my program finishes earlier. This is the cloud time. So saying that if during the cloud time, that my server goes really high frequency to get the job finished earlier, although I'm having a lower energy consumption. But because it's cloudy, so I cannot rely on solar power. So it turns out that you will use more carbon footprint emission. For example, gas-based power plant to generate your power. So it turns out you are going to emit more carbon footprint at this time rather than the time you have a lot of solar power. So right now, I'm also going to show you a demo. Not sure if it's working because our servers were down earlier. But let's see if this machine is still being able to connect it. Am I still able to reach it? No! Okay. Wait, let me see. What can I do? How can I interrupt? Okay, so let's try. And let's try to see if I can reach that machine. All right. Okay, so but this machine is right now not reachable. But let's see the priori run of this. Okay, the priori run. Let's check the priori run. So previously, I have used a program to run a matrix multiplication. And this is the same matrix multiplication program that you guys has seen. And I lower the maximum frequency, and I use a program called Liquid to see the power and energy consumption when I run this program. So what you can see here is that with lower frequency, the program takes 22 seconds to execute. And this line, it tells you the maximum and the minimum frequency that we have during the runtime. So it's actually, maximum and minimum here, and this is the average. So the maximum is 800, and the minimum is 474. So we are actually operating the processor at a very low speed. And this processor's top speed, as far as I remember, is something like 2.8 or 3, right? So this is lower than 30% of its top frequency, right? So how much power it drains? So the power consumption here is the power state. Read this one, right? The power state is 20, the maximum, right? And let's see, the total power consumption, the total energy consumption is 445, right? So that's what it tells us, right? But right now, if I am able to restore it to the maximum frequency, right? So what you will see, right, is the frequency can be as high as 3 gigahertz, and on average, 621, right? A lot higher frequency, right? And the power consumption at a peak is 28. And read this, at a peak, 20. What does that mean? Even I lower the power consumption, the frequency to just 800, it only gives you a watt drop, right? So that describes operating at 30% of the frequency can still consume more than half of your power consumption, because a lot of people try to argue that with me in the very beginning. But let me just show you the truth, right? There's nothing debatable here. That's the fact, right? It's something like you would never argue with other people, 1 + 1 = 2. This is the reality, right? So because of that, right, with the capability able to run your processor at 3 gigahertz will only consume 7 seconds, right, which is 3 times faster. And look at this, your power consumption is actually not going down by 3 times. So the total energy consumption of the upper part is 445, but for this one is 174. So lower power consumption doesn't give you better energy consumption, right? So that's something you should learn from this demo, right? So, right. So, and the other thing, and what's the main reason? Because if you lower the frequency based on the formula, you can only reduce the active power, right? So what's the other thing that would imply? Is active power the majority of power consumption now? Is active power the majority of the power consumption now? The answer is no. Right? Look at this. We lower the frequency to be even lower than 30%, but we are not even seeing half of the reduction, right? So what does that mean? A majority of the power consumption actually comes from the other side, the leakage power. And again, what's the source of the leakage power? It's not because you are operating. It's because you are powering on the transistors. Even though they are not doing anything, it will still consume leakage power, right? And if you imagine that, that explains why when you increase the density, or why when you use a new, more advanced process technology, the power consumption doesn't go down. Because the more transistors you have, the more leakage power you have, right? And active power is only a small fraction in your power consumption, right? So based on this, 2 of them is correct, right? Lower the frequency help reducing the heat generation. And operating at 30% of peak frequency can still consume more than 50% of peak power. The demo tells you, right? Okay, so what does that mean is that slowing down all of them is potentially not a good option, right? So either slowing down all of them is not a good option, or slowing down some of them is not a good option. So we have to think about new type of parallelism, right? So we have talked about the data level parallelism, right? And through vectorized processing, right? And another place we find a lot of vectorized processing is actually in computer graphics, right? So if you look at the basic concept of shading, right? It's basically going through a set of vector operations like this. And if you look at the vector operations they need, right? It's vector inner product and a vector element-wise summation, right? So this is the very basic C code for performing a tone shading, right? So based on this, if today I want to design a spatialized processors for computer graphics, what that processor should look like. All right, so let's take a look. Okay, so apparently a lot of you guess is C. So why don't you guys go ahead and discuss with your friend to see what should be the answer. All right, let's take a look. What do you guys think about the GPU design? Okay, C, still 2. Okay, what are the 2? Should the architecture render pixels as fast as possible? Why not? You care about the throughput. Okay. Should it need a branch predictor, a branch unit? Not necessarily, right? Because if you look at the code, right, the code right here, do we really need a lot of branch predictor, right? Because they are just vector operations, easy to predict, right? Okay. How about powerful array of ALUs? Yes? Okay. Should offer very large bandwidth of memory accesses? Okay. So your yes is basically saying 3 and 4. 2 and 4. But I also heard some people say 3. Right? So what are this? So first of all, right? Why don't we need very fast pixel render? So here's the reason. You talk about throughput, but I would have a different perspective for that. If you check about the demand, right? So again, when you design your architecture, you should always thinking about what's the demand of your applications. So for computer graphics, let's say you have full HD, right? Then each pixel, and you want to deliver 60 frames per second, right? Then even for like 120 frames, you only need to generate this result within 8 milliseconds, which is equivalent to 800,000 cycles, even though you're just operating at 1 gigahertz. Right? So what does that mean? You have abundant of processor time to generate those results. And for computer graphics, it doesn't really matter when are you going to give out that result, as long as it's at the time before your eyes need to see it. And if you deliver it after, it doesn't make sense. If you deliver it earlier, it doesn't make sense either, right? So what that means is that we just need to have the processor at the right speed to deliver that performance, right? So even though, okay, you say we are now in the era of 4K, right? So you divide it by 4, right? You still have a lot of cycles, right? So what does that mean is you do not render this processor as fast as possible. You don't need branch predictor because you have pretty regular code. And check the amount of operations that you want is simply multiplication and addition. So you don't need powerful LUs, right? So a lot of people, they have the misunderstanding. They think GPUs are very powerful processors. The answer is no. Right? Based on the spec that we just showed, they can only perform limited amount of operations, multiplications, additions in general, because that's what the graphic processors would need. It doesn't deliver results at the shortest latency, because for the sake of delivering your graphics, we don't need, right? And it doesn't need to support that many operations. It doesn't have a branch predictor. We do need a large bandwidth because the amount of data it has to process within a given period of time is actually pretty large, right? So what is an appropriate GPU architecture? So first of all, you need a vector processing model, right? So like those vector architectures that we introduced makes a lot of sense. Simple LU operation. So your LU can only support very few instructions, almost no branches. And it's deadline driven, throughput oriented. So you can make your LUs really slow. Really slow LUs, we need a lot of them. Sounds like a good thing to implement in dark silicon era. So that explains why we are now in the dark silicon era, but we still see GPUs making improvements in their performance because they are originally really slow already. So they have the room to grow, right? It's not because GPU architecture or GPU is more severe, severe than others, just because they are originally really, really slow, right? So here's the modern GPU architecture. So typically you will see they still have the memory hierarchy, and within each, they have a lot of LUs. And these LUs, they can only perform the same operations at the same time within the same processor core. And because each processor core, they only share a single control. So they can also save the logic of control. And each processor core here is basically a vector processing unit. And depending on the operations that you need. So for example, if I am performing a lot of floating point 32 operations, I can optionally turn off my FP64 or integer 32 transistors or the tensor cores to save some power, right? So that's the microarchitecture of GPU nowadays, because it better fulfill the limitations in dark silicon era, right? Because in dark silicon era, you can only make your transistors slower. And for GPUs, we do need a lot of them, and we don't need a lot of them to be fast, right? So it's a way that we can fully utilize the silicon, right? And so that's the GPU architecture, right? So so now let's review this, right? In modern computers, with the additions of GPUs, right? You can think about we are adding two different types of parallelism on these machines using this GPU. So first, you can exploit data level parallelism by using the vector processing unit within each streaming multiprocessor. And thread level parallelism, if you are allowed to use multiple streaming multiprocessor at the same time, then you also can exploit thread level parallelism on GPU. So GPU is also a new vehicle of carrying data level parallelism and thread level parallelism. Okay, however, I do want to counter argue with Jensen Huang a little bit. He keeps saying that they can follow the Moore's law. However, I would say it's a company that's cheating. If you check the power consumption, right? This is from their spec, right? If you check the power consumption between Ampere architecture and Hopper architecture, you'll figure out, yes, they indeed scale up the transistors. However, the power consumption goes up even more significantly. So what does that mean is that they do not surpass the limitation of Dinadian scaling. They follow the Moore's law by using more advanced architecture process technology by TSMC. But what does that imply? This implies two things. First of all, TSMC is still able to scale down the size of transistors based on Moore's law. But if you check the power consumption per transistor, they are actually making per transistor power consumption even worse with their new technology, right? Like per billion transistors with their old process technology is 7.3. With the new technology is 8.8, right? So if you're a company like Intel, they don't want their fab to produce that kind of transistors. That's why they refuse or they struggle with the new process technology, because they want to roll it out before it's mature. People from Wall Street, they don't know this, right? So that's why those managers, they mess up the company like Intel, right? So sometimes you do need a CEO that knows the technology better to do the right thing. All right, but on the side, right, GPU or many core processors improve the throughput per chip through providing massive parallelism where each processor at a lower speed, but still not ideal, because remember, each of the LU is still running at a very, very low frequency. So if you have a latency sensitive workload, you still have to rely on your CPUs. All right, so before you leave the classroom, a few things that I need to let you know. So first of all, tomorrow I will have my last office hour before the final exam, and submit a proof of your participation, in the course evaluation through Gradescope would give you a full credit reading quiz. And assignment 5 and programming assignment 3 due this Thursday. And more details about final exam, it will be at the same time as it's scheduled by the school, but it will be online. So you can find a very comfortable room to take the exam. And because it's online, I'm not assuming you guys going to close the book. So, but what does that mean is that with this format, I'm able to give you more open-ended questions. For example, I would be able to ask you to look up the paper online and figure out the detail yourself, right? Question? Is it 7 p.m.? Yeah, 7 p.m. That's what the school scheduled. That's what the school does, right? And the reason why we have to follow that rule is that we can make sure this time is not overlapping with any other of your course. I'm sorry about that, but that's what the school does. That's not my decision. Yeah, okay. What? I mean, I cannot control that, right? Because it's not something I can decide. All right? Other than that, enjoy the rest of your day. I will see you on Thursday.